Okay, let's talk a little bit about nuclear fission versus nuclear fusion, because these are both terms that you've probably heard before, and they both are processes that involve radioactive materials and nuclear chemistry in general, but they are very different in terms of the way that we use them, or can use them, at least here on Earth. So, nuclear fission is the splitting apart of a nucleus into smaller pieces. And this could be into two pieces. We could kind of split it almost in half. It doesn't really matter. There's different fission products that come about through this process, and we'll talk about it in more detail. But fission is splitting a larger unstable nucleus into smaller pieces, again with the goal, just like any radioactive process, to become more stable. So you have a larger unstable nucleus that you split apart into smaller pieces. That's nuclear fission. It takes a little bit of energy to put it in and split it apart, and you get a lot of energy out once the process occurs, and we'll talk about how that is in just a second. Now, nuclear fusion, on the other hand, is the fusing together of two smaller nuclei into one larger mass. Now, this requires a lot of energy, and if you've heard of things like particle colliders, then if we take two smaller nuclei and bash them together, so we have kilometers worth of distance that we're accelerating these teeny tiny particles over in order to bash them together and fuse them together, then that's kind of what we're talking about, nuclear fusion. Again, literally talking about the fusion of a nucleus. So let's talk a little bit more about both of these processes, starting with fission. So nuclear fission. Nuclear fission is the way that we get nuclear power here on Earth. So nuclear fission is what we see in nuclear power plants. And fission reactors are the reactors in nuclear power plants. Around 20% of our electricity right now comes from nuclear. That's here in the US. So, that's not a huge number. We have a lot of other ways that we get our energy, but about 20% of our power comes from nuclear. Now, there's other countries that are 100% nuclear powered, like France, for instance, has 100% nuclear power, and there's others that are quite large in terms of percentages, and they're doing just fine. The concern with nuclear power in general is just that it'll undergo a runaway process where we have a chain reaction that occurs, and you won't be able to stop it, and things melt down because there's so much energy being produced. And so let's talk about how we can model that. The way that we model fission comes from a scientist by the name of Niels Bohr. And we've seen Niels Bohr before with the Bohr model of the atom. The Bohr model of the atom had electrons that were represented in shells, so these different energy levels. And Niels Bohr also modeled fission, and he called his model the liquid drop model. Liquid drop model. And he said, basically, we can envision a nucleus as a drop of water. So here's our drop of water. I like to visualize our nucleus as a drop of water here, like a drop of water on a piece of waxed paper. If you guys ever played around with that, where you put a big drop of water on wax paper, and you can kind of move the wax paper around and the liquid droplet moves around, that's what I envision when I'm envisioning his liquid drop model here. So here's my droplet of water. I take a high energy particle like a neutron, and I shoot it at my nucleus here. And this neutron then is going to start working its way through the droplet. So it's moving faster, it starts to deform my droplet here, it's pushing its way through, So now I have this thing that's pushing its way through, and now it will cut clean through, and now I'm left with 2 particles, and my neutron goes straight through. Now, in the process of doing this, in my liquid drop model here, in the process of shooting this neutron through, what I've ultimately done is I've taken a large nucleus that's less stable because of all the extra protons in there, and I've made it into 2 smaller nuclei, and the 2 smaller nuclei have fewer protons, and they're inherently more stable. So if I have more stable nuclei here, I need fewer neutrons sitting around to help hold things together. So in the process, we usually lose a couple of neutrons also. So now I might have a nucleus like this. If this was, let's just say, uranium-235. Uranium-235 is a common isotope of uranium, and it has 92 protons because it's uranium, and it has then, if I subtract that from my mass number, it has 143 neutrons. So as this neutron is busting through my uranium-235 nucleus and busting it into 2 pieces, now I have a piece that's, let's just say this one has 36 protons and 55 neutrons. And this bottom one, let's say it has 56 protons and 86 neutrons. So the one on the top here, 36 protons, if you look at your periodic table, 36 corresponds to the noble gas krypton. So this is the isotope krypton 91 here. So this is Kr for krypton. And then the bottom one is barium. So barium is number 56 on the periodic table. Barium is one of our alkaline earth metals. So barium has 56 protons. So this is the isotope of barium, barium-142, because I added together my 56 and my 86 there, and I ended up with 142. Now if we look at our math here, then 56 and 36, when I add those together, it gives me 92 protons. So the number of protons I ended with is the number of protons I started with. That's a good law of conservation of mass thing. Now, because I have fewer protons, I need fewer neutrons to help glue them together. So we said that when we have a lot of protons in a small amount of space, then they're going to want to naturally repel each other, and so I need some neutrons in there to act as glue. So I need fewer neutrons here, and then here I have 56 protons, so I need 86 neutrons, a few more, but when I look at the math here, when I add together my 86 and my 55, that gives me 141, and so the other 2 neutrons that are lost from the initial isotope came out when I broke them apart, when I broke them into pieces. So this took some energy to occur at the beginning because I had to accelerate this neutron with enough speed and enough velocity here to push through my nucleus, and then it's still going to be moving pretty quickly on the way out. And because of this process, when I separate these guys are going to start moving pretty quickly as well. Now this is important because now if we're picturing what happens with these neutrons, so here's my neutrons that came off in this process, the original one and the 2 from the splitting apart of my atom. Then now each of these can go on and split another nucleus. So here's another nucleus that it splits into 2 pieces, and then we have more neutrons coming out from there. This one splits this guy. Now it splits apart into 2 pieces, and now I have neutrons coming out here. This one splits apart this guy, etc. And now we have neutrons coming out here. Etc. And then these guys can go on to split 3 more, these guys can go on and split 3 more, these guys can go on and split 3 more, and now we have what is called a chain reaction. And a chain reaction is just any process by which the products of the original reaction are going to continue that process over again. So whatever you form in that initial process is going to keep the reaction going. It's kind of like the Greek monster, the Hydra. The Hydra is the thing where if you hack off one of its heads, then 2 heads or 3 heads grow in the place of it. My Greek mythology is a little bit rusty, but you guys know what I'm talking about. So you cut off the head of the monster and 2 more grow in the spot. It's kind of like that, so a chain reaction. Another good way to see this is if you just YouTube chain reaction videos. They usually will do them with things like mouse traps and ping pong balls. So you have a bunch of mouse traps that are set up with these ping pong balls, and then they take one ping pong ball, think like your neutron here, and throw it into the whole array, and that gets everything else started, and that moves everything else. And when it does that, then all of these things are moving around, and that motion is kinetic energy, and we get all of this energy that comes out because of this chain reaction. So this chain reaction and the energy therein is really what we are harnessing in order to give us nuclear power. So this is our energy source here. All right, so that's fission. Now fusion, we said, is putting together 2 smaller nuclei into a larger one. So if I accelerate 2 small nuclei together, so I smash them together and I end up with a resulting nucleus here. If I have a small nucleus here and its mass is m, and this one also has a mass of m, this one right here and this one right here, so they're both of equal mass, they're both made up of the same amount of matter, then when I put them together, the law of conservation of mass says that the mass of this resulting nucleus should be 2m. Is everyone with me? So I have 2 m's here that I'm smashing together, so I should end up with 2m. But it's not. It's smaller than 2m. And the reason that it's less is because there's so much energy produced, and I'm going to just call that a wave here. So much energy is produced in this process. You have to slam these 2 things together with a lot of energy, and then once you do, the resulting nucleus is going to eject a bunch of energy. And then when I look at the relationship between the 2, then what I thought should be 2m is slightly less because of the energy that is lost. And there's a relationship, a famous relationship, between mass and energy that was made by a guy who is probably fairly familiar to you, and that would be Albert Einstein. And Albert Einstein said, well, this energy and the mass are related to each other, and they're related by the speed of light squared. So E here is for energy, M is mass, C here is the speed of light, which is a constant. And so energy can be converted into mass, and mass can be converted into energy. That's what Einstein said with E equals mc squared. Now, you probably know Einstein for his theory of relativity, and he was all about kind of regular Newtonian type physics, which are grounded very much in the physical characteristics of our universe and our world. So we can see things, the cause and effect relationship between things. That's really what physics is all about, is the interrelatedness between cause and effect. And Einstein looked at this and said, okay, well, if I'm thinking about this like a god, for instance, then we don't need probability. We have patterns for things. There's obviously relationships that are fundamental to the way that our universe works. And so he famously says, and you guys might have heard this quote before, God doesn't play dice with the universe. That's what Einstein says. God doesn't play dice with the universe. And it was a little bit of a dig at Niels Bohr. Niels Bohr, with his Bohr model of the atom and talking about nuclear fission, he believed in quantum mechanics. That's the idea that energy can be in discrete packets, and that things like atomic orbitals give us the probability of where we will find things on an atom, for instance. And so he really believed that probability, it really has to govern our understanding of the universe, and that we can never really be certain about everything, and that we're limited by our own observational skills. So Einstein says God doesn't play dice with the universe, right? We have to have order, we have to have structure. And Niels Bohr famously said, well, Einstein, who are you to tell God what to do? Which I really like. They used to debate together, and I thought that would have been a really fun thing to have witnessed. But they were also very good friends as well. So that's nuclear fusion and nuclear fission. The key here is that for both processes, for both fusion and fission, it requires a lot of energy to make them occur, but you get so much energy out that it does make it worth it. We have not been able to do nuclear fusion on Earth in any sort of efficient way. We can do it, but we can't do it and get enough energy out compared to the cost that it would require to put it in and make it useful in terms of our own energy consumption or use. Nuclear fusion is the type of thing that's done at the core of a star, for instance. So all of the elements in the universe were originally in the cores of these hot stars that were making and fusing together nuclei to get larger and larger elements. So that's how the elements were first created in the beginning. And so fusion is a process that requires an incredible amount of heat and pressure and energy, and we just haven't found a way to use that and harness it here on Earth for our purposes. But we can use fission because of this idea of a chain reaction and the amount of energy that we get out once we just start the process going. So I hope this helps to clear up kind of those two processes, gives you some more information about where we get our nuclear power, and if you have any questions, as always, please don't hesitate to contact me.